Right, let's get started. So, hello everyone, this is SeungryongKim. So today we will finish lecture 11 and we'll move to the lecture 12. So, so in this semester we will cover by lecture 13. So here, single value decomposition. So we are here, lecture 11, least square. After finishing this lecture, the lecture note, we will move to the lecture 12, Eigen vectors and eigenvalues here, and we'll finish this semester by talking about singular value decomposition. Okay. So the last week we discussed the least square solution. So what was the least square solution? Okay, let's review. So it was chapter 6.5. So least square problems like that, inconsistent system Ax equals B that has no solution arise often in the application. So in this case, we want to find out approximative solution, which was called generalized least square solution. So how to find out the approximate solution? So to answer this question, we have to know that this least square solution definition looks like this. So blah 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 blah. After that, we have to find out x hat that satisfies this inequality. So this one, x hat, is the orthogonal projection of the B, vector B, onto the column space of matrix A, which was another subspace, subspace. So yeah, here x hat was the least square solution. So yeah, then B hat was the projection of the vector B onto the column space of matrix A. Right? So when we compute this one, blah 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 blah, then we finally achieve the A transpose A times x hat is equal to x transpose times B. In other words, the solution of A transpose A times x hat equals to A transpose B is the least square solution for the Ax equals B original matrix equation. In this case, this equation is called normal equation. And solution of this is often denoted by x hat. So solution of the general least square solution problem is that the solution of this normal equation. All right. Yeah. So it was theorem 13. Set of the least square solutions of the Ax equals B coincide with the non-empty set of the solution of the normal equation is ATAX equals to ATB. This is the least square solution. All right. Today, let's see the examples for the least square solution. Okay, so the question was the finding least square solutions of the inconsistent system Ax equals B for A is equal to equals to looks like this, B equals like this. First of all, in this case, there's no solution for the Ax equals B, but we want to find out approximate solution, least square solution. So first of all, how to do this? We have to view normal equation. So A transpose A times X equals to A transpose B, vector B. Okay, so first of all, A transpose A, it's going to be, this is A transpose and this is A, then these two matrix multiplication, AT by A, is going to be the 17. So 17 was computed by first row and first column. This one is going to be the first column, first row and second column. So it's going to be 1, blah, blah, blah. And ATB is going to be the AT, 그렇죠? Transpose matrix A and B here. And which is going to be first row times first column. So it's going to be 19. So second row times first column is going to be 11. So ATA is going to be 17, 1, 1, 5, and ATB is going to be 19, 11. 그렇죠? Then normal equation, our normal equation is going to be this one, 그쵸? ATAX, 그쵸? And ATB here. 그쵸? So in this case, from here, we know this solution is now consistent. 그쵸? Then we can use any kind of solution solving skill to solve this kind of consistent system. 그쵸? In this case, because this is the ATA and this is the ATB. So in this case, let's use inverse of matrix ATA. So inverse of ATA was 1/84 times 5 -1 -1 17. So please try to derive yourself. Anyway, this is the inverse of this matrix. Then solve this normal equation. Then it's going to be A hat equals to inverse of the ATA times ATP, where inverse of ATA was here, and ATP was 1911. I will just keep the complicated computation. So if you want to follow in details, please solve yourself. Okay. Anyway, we will further derive this one by 1/84 times 168, which is going to be 1, 2. Then our least square solution x hand is going to be the 1, 2. This is the least square solution. Okay, that's it. And here was the theorem 14 about least square solution. Let matrix A be an n by n matrix. The following statement are logically equivalent. So first of all, equation x equals b has a unique least square solutions for each b in Rm space. This is the first statement. The second statement is the columns of matrix A are linearly independent. Third one is matrix A transpose A is immutable. In this case, these three statements are whole logically equivalent. I mean, whole true or whole false. This is the theorem 14. So we can prove this one very intuitively like this. First of all, if the columns of matrix A are linearly independent, we already know AX equals 0. Homogeneous system has trivial solution. Trivial solution. Then by multiplying A transpose left-hand side and right-hand side, A transpose AX equals 0 is another our matrix equation. In this case, this one still has trivial solution. It means that ATA is invertible matrix because ATA is square. It is square, so ATA is invertible. Right, invertible. In other words, if ATA is invertible, then these statements are true. Then AX equals 0 also true. Then columns of matrix A are linearly independent. In other words, these two statements are logically equivalent. Then from the numerication, I mean AT numerication ATA X equals to ATB. Because ATA is immutable, there exists the inverse of matrix ATA by IMT, 그쵸? Inverse matrix theorem. Then we can uniquely find the solution of this equation, numerication, by inverse of ATA times ATB. So the least square solution is unique. So AX equals B has a unique least square solution. This is a theorem 14. Please remember that you don't need to memorize all the proof, but please understand high-level meaning of this theorem. Each theorem, in this case, when columns of matrix are linearly independent or matrix ATA is immutable, then least square solution is unique, which was the inverse of ATA times ATB. This is uniqueness of the least square solution. 자, 한국어로 더 설명을 하면, 여러분 우리 이제 least square solution을 저번 주부터 하고 있었고요. inconsistent system, 여러분들이 가지고 있는 AX equals B가 inconsistent한 경우에 여러분들 그래도 솔루션을 찾기를 바라는 경우가 많다고 했죠. 그런 경우에 이런 least square solution 찾는 거고, 이런 AX equals B가 아닌 이런 노멀리케이션 풀면 되는데, 문제가 뭐냐면 이 ATA가 인버터블하면, 즉 인버스가 존재를 하면 그냥 얘는 유니크하게 이렇게 찾을 수, 바로 이렇게 찾을 수가 있더라, 디터미니스틱하게 찾을 수 있더라 라고 하는 게 이 theorem의 얘기였고요. 언제 인버터블 하냐? 컬럼스 매트릭스가 리니어 인디펜던트하면 방금 말한 프로퍼티들 때문에 이게 만족한다 라는 거죠. 그 말은 뭐냐? 여러분들이 어떤 AX equals B를 만났어요. 그렇죠? 근데 AX equals B가 솔루션이 없어요. 그렇죠? 근데 매트릭스 A를 봤을 때 얘의 컬럼들이 리니어 인디펜던트 해버리면 이 솔루션은 리스퀘어 솔루션 유니크하면서 이렇게 살 수 있다 라고 하는 게 바로 이 theorem에서 말하고 싶은 거죠. 알겠죠? Question. No? Okay. So let me show you example. By the way, our final exam date is not determined yet. So I will let you know soon, but it's not determined yet. Okay? Maybe after 2 weeks, maybe, but let me know. Let you know soon. Okay, so this is example. Find the least square solution of x equals b, where x equals like this, b equals like this. So to solve this least square solution, maybe you can use this numerication, right? This numerication, similar to previous example. But if matrix A has the special form, you can easily solve this least square solution. In other words, okay, when you see columns of matrix A, let's say first column is A1 and second column is A2, then columns of the A1 and A2 of matrix A야 orthogonal. 그렇죠? This is special form. How can you know that? By computing the inner product between A1 and A2, which is going to be 0. So we already know A1 and A2 are orthogonal, right? Then orthogonal operation of the B. Orthogonal operation of B onto column space of matrix A can be directly computed by this equation, right? So we already talked about this one in the orthogonal projections. 그렇죠? This is just the equations, 그렇죠? For the projection of matrix vector B onto subspace W, in this case column space, then you can easily compute this one. Because A1 and A2 are orthogonal, so A1 and A2 are orthogonal basis, so you can easily compute this one. Because you already know P, vector P, and A1 and A2, then you can compute the P hat by using this equation. So by computing this one and this one from here, it's going to be 8 over 4 times A1 plus 45 over 90 times A2. Then from this one, A1 and A2, we can find out blah 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 P hat at -1, 1, 5 over 2, 11 over 2, 11 over 2. Now that P hat is known, we can solve AX equals P hat. Here, X hat was least square solution. Square solution. AX hat is equal to P hat. It's going to be this one, 그렇죠? This one. From here. This one is going to be x1 and y1. Coefficient of the each vector is common vector. So this one, coefficient can be the x hat. So this is the least square solution. This is another way to solve the least square solution when columns of the A1 and A2 are orthogonal each other. Then you can easily find out the least square solution here. Okay. Question. 자, 여기까지 어렵지 않죠, 여러분? 그 least square solution을 푸는 얘기였고요. 일단 우리 한번 끝내봅시다. So in some cases, the numerications for the least square solution problem can be ill-conditioned. It means that if you want to find out the least square solution by considering the ATAX times ATB, in many cases, ATAX times AT can be ill-conditioned. That is, the small errors in the calculation of the entity ATA can sometimes cause the relatively large errors in the solution X hat. In other words, if there are errors in computing ATA, when we compute inverse of the ATA times ATP, the relatively large errors in the solution in X hat exist. So, in general, least square solution can often be computed more reliably through the QR factorization of matrix A. So, here. So, this is theorem 15. Given n by n matrix A with linearly dependent columns, if the matrix A has linearly dependent columns, then we already know matrix A can be decomposed as a QR factorization by K and R. Then for each B in Rm space, equation Ax equals B has a unique least square solution given by X hat equals to R inverse times Q transpose P. This is the alternative calculation of the least square solution. In many cases, if ATA has some error, this one can be more can provide a more reliable solution compared to the original normal equation based method solution. In special case, then if matrix A has linearly independent columns. 그래서 한국말 설명하면은 매트릭스 A가 리니어 인디펜던트한 컬럼을 가지는 특이한 케이스인 경우는 우리가 이제 알고 있죠? 이 매트릭스 A가 QR로 팩토라이즈 될 수 있다는 걸 알고 있으니 QR 팩토라이즈가 돼버리면 이 A 햇이 R 트랜스포즈 QT B로 아주 쉽게 풀릴 수가 있고 이런 솔루션이 ATAX equals to ATB 즉 노멀 이퀘이션 푸는 것보다 훨씬 더 릴라이어블하게 솔루션 찾을 수 있다라는 얘기를 하는 거예요. 물론 우리가 그냥 손으로 푸는 건 사실 별 상관이 없는데 여러분들 어쨌든 이 리니어 알제브라라는 거는 결국에 어떤 프로그래밍을 해야 되기 때문에 이런 에러에서 더 강인하게 풀 수가 있는 솔루션이 결국 QR 팩토라이제이션을 사용하는 거다라는 거죠. 그렇죠? Let's prove. First of all, let x hat equals to inverse of the R times Q transpose B. Then original equation AX hat. Oh, sorry. 꺼졌네요. 잠시만요. Sorry about that. Okay. So then AX hat is going to be the QRX hat. 그렇죠? QRX hat because A is equal to QR. 그렇죠? Then if X hat is like this one is going to be the QR R inverse Q transpose B and QQT times B. 그렇죠? 그렇죠? Because this one is going to be identity matrix. 그렇죠? Then columns of matrix Q form a also normal basis for the common space of matrix A. Hence QTB is the orthogonal projection of the P hat OP onto column space of matrix A. 그렇죠? We already talked about this one in end of lecture 9 이었나? 그렇죠? 여기서 그렇죠? 이거죠? UTY 그렇죠? So AX hat equals B hat, which shows the X hat is a least solution of AX equals B. So X hat was unique, 그렇죠? Following the previous theorem. So in this case, this one, X hat is equal to R inverse QTB, is going to be our least solution when matrix A can be QR factorized. In other words, matrix A has the linear independent column. Then our least solution can be X hat is equals to R inverse Q transpose P. This is the alternative calculation of the least solution. Okay? All right. So this is the least solution. That's it. Is there any question about least solution? 자, 우리가 조금 시간을 많이 썼는데 이렇게 해서 우리가 이제 리스큐 솔루션이 존재하지 않는 경우에 솔루션을 어떻게 찾을 건가에 관한 얘기를 좀 나눠봤습니다. 그렇죠? 자, 여기까지 혹시 질문 or comment or question? Nope. Right. Then, if not, we will move to the lecture 12 and lecture 13. Eigenvectors and Eigenvalues and singular value decomposition. Okay, so this is a chapter 5.1, Eigenvectors and Eigenvalues. Eigenvectors and eigenvalues concept can be used so many kinds of computer science field. For example, like the dynamic system or differential equation or the Markov chain, something like this. So yes, this concept is one of the most important concepts in computer science department. So yeah, eigenvectors and eigenvalue let you know about most of things of your linear transformation or x to the ax matrix multiplication. Okay, let's deep inside. So even though this is chapter 5.1, we have to start with determinant because we have to know the determinant in this chapter 5.1. But here we'll just briefly mention what determinant is. Then later we will talk about how to use this determinant to compute eigenvalues or eigenvectors. Right. So first of all, in previous lectures, we already talked about determinant. 그렇죠? In previous lectures, we talked about determinant of the 2x2 matrix. 그렇죠? 2x2 matrix. What was the determinant? This determinant concept was related to the invertible matrix. 그렇죠? What's that? We discussed that 2x2 matrix is invertible if and only if determinant is non-zero. For example, if the matrix is invertible, then inverse can be found as follows. When matrix A is A, B, C, D, inverse of matrix A was 1 over AD minus BC, and T negative C negative B A. So in this case, we called determinant of matrix A was AD minus BC. 그렇죠? 여기였죠? Then to make this exist, I mean the inverse of the matrix exist, this one should not be zero. So this was the concept of the determinant. In other words, if determinant of matrix A is zero, original matrix A is not invertible. This is the concept of the determinant. Then the question is, okay, so 2x2 cases, we can easily find out AD minus BD. It was just the definition. Then question is, how can I find the determinant of a larger scale matrix? For example, like 3 by 3 or 4 by 4 or blah, blah, blah. This is the determinant of the larger matrix. All right. So, first of all, how can I determine matrix A is invertible? So to answer this, if matrix A is 3 by 3, A11, A21, A31, A12, A22, A32, A13, A23, A33. Then to answer, to find out determinant, we first row reduce this original matrix to the echelon form. Then this one, this triangle as a determinant. We will define this triangle as a determinant. Oh, by the way, from this slide, we will talk about determinant concept here and here and here and here and here, like this. First of all, to understand, to solve the eigenvalues for eigenvector, you have to know determinant. But in this semester, the determinant will be out of scope, so we will just briefly mention what determinant is. So you don't need to memorize all the determinant concept. Please just high level understand what determinant is. 자, 우리 지금 여기 10페이지에 거쳐서 이제 우리가 determinant라는 게 무엇인가를 조금 얘기를 할 건데 뭐 좀 어렵죠? 막 내용이 좀 복잡한데 몰라도 돼요. determinant라고 하는 몰라도 되고 여러분들 그냥 determinant가 이런 거다라는 것만 이해하면 되고요. 우리가 원래 실라버스에 이번 학기 determinant까지 하기로 했는데 조금 이번 학기 그러니까 이제 여러분들이 좀 다뤘던 내용들이 좀 많아서 determinant는 우리가 뭐 크게 중요하게 다루진 않을 거예요. 뭐 이제 조금 더 구체적으로 얘기하면은 뭐 시험 범위에 들어가진 않을 거니까 여러분들 그냥 편하게 determinant가 뭔지 이해해 주시고 이제 요게 아이겐밸류, 아이겐벡터를 이제 나중에 이해할 때 아 이런 컨셉들이 쓰이는 거구나 정도만 여러분들 이해하면 돼요. 알겠죠? 뭐 이게 좀 막 복잡한데 여기 너무 스트레스 받을 필요 없어요. 그렇죠? 오케이. Anyway, let's go back to the determinant of the larger scale matrix, in this case 3 by 3. Then first of all, let's row reduce the original 3 by 3 matrix, blah, 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 blah. Then we can make the echelon form. And here, this triangle is going to be this kind of equation. You can easily follow this one. Then, since A is invertible, this one must be non-zero. If this one, triangle is zero, A equals B does not have solution. So if A is invertible, this triangle should be non-zero. So in this case, we called this triangle as a determinant of a 3 by 3 matrix A. So first of all, 2 by 2 case is our determinant is going to be AD minus BC, and 3 by 3 case is this complicating equation A111, A222, A11, A22, A33, blah, 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 as a definition of the determinant for the 3 by 3 cases. Similarly, we can define larger scale matrix. For example, determinant A was the A11, A22 minus A12 times A21 for the 2 by 2 matrix. And 3 by 3 matrix was the scale triangle and blah, 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 blah. Then we can reduce this one as A11 times determinant A, large A11 minus A12, small A12 times determinant large A12 plus small A13 times determinant of A large A13. Where A11, A12, A13 are obtained from the matrix A by deleting the first row and one of these three columns. Let's skip this one. Yeah, let's skip this one. Blah 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 blah. And finally, anyway, for the 1 by 1 matrix, for example, A was the small A11. Determinant matrix A is going to be the A11. 그렇죠? If n is equal to n is greater than and equals to 2, determinant matrix n by n matrix is the sum of the n terms of the form plus minus A1j, determinant A1j with plus and minus sign alternating where entities A11, A12, A1n from the first row in matrices. So in symbols, determinant A is going to be accepted. You don't need to know or understand this one, but anyway, there is the way to find out determinant of matrix A larger than 2 by 2. This is the determinant. In other words, if you know the so this is example. If you have the matrix A, you can find out determinant by following this equation. So it's going to be the blah blah blah. So determinant A is not determinant A is going to be 2. So first of all, what's the meaning of the determinant? So in other words, determinant A is not equal to 0, A is invertible. In other words, determinant of matrix A is equal to 0, A is not invertible. So in eigenvalue and eigenvectors, we will use this concept. And determinant has some properties. For example, determinant AT is going to be the determinant A times determinant B, and determinant of A transpose, which is equal to determinant of A. And if A is a triangle, then determinant of matrix A is the product of the entries on the main diagonal matrix A. We will not prove all the properties, but we'll just use these properties to derive eigenvectors. So, yeah, let's move to the eigenvalues and eigenvectors. 자, 뭐 되겠지만 여기까지 여러분들이 제가 이제 이 디터미넌트까지 여러분들 이번 학기에 몰라도 될 것 같고요. 디터미넌트라고 하는 게 이런 거다. 결국에 어떤 매트릭스 A가 인버터블한지를 알려면 이 디터미넌트 A가 0보다 같은지 같지 않은지로 볼 수 있고, 그 디터미넌트는 어떻게 구하냐? 뭐 이렇게 구할 건데 여기까지 여러분들이 몰라도 된다. 그렇죠? 이거는 이런 수식으로 구하면 되는데, 이거는 여러분들이 그냥 있는 수식을 쓰면 될 거예요. 그렇죠? 그리고 만약 시험 범위에도 요거는 우리가 그냥 주어질 거고요. 근데 일단 프로퍼티들이 있어요. 프로퍼티들이 있는데, 어떤 매트리스 곱은 디터미넌트 A, B는 디터미넌트 A 타임스 디터미넌트 B고, 디터미넌트의 A 트랜스포즈는 디터미넌트 A고요. A가 트라이앵글이면은 디터미넌트 A는 product of the entries on a main diagonal. 그 메인 다이고널에 있는 애들의 곱으로 이루어진다 라는 이런 프로퍼티들을 그냥 우리는 사용을 할 거예요. 그렇죠? 여기까지 이제 우리가 다 증명하기에는 이번 스컵이 너무 많으니까 이렇게 진행을 하면 좋을 것 같아요. 알겠죠? Then let's move to today's topic. Eigenvectors and Eigenvalues. So, to understand this, we have to focus on this terminology, Eigen. Eigen means characteristics of a matrix, characteristics of matrix. In Korean, 특징, 그렇죠? 특징 이런 뜻이에요. 그래서 어떤 매트릭스의 characteristic 또는 매트릭스의 eigen characteristic 특징이라고 하는 것, 즉 매트릭스가 어떠한 특징을 가지느냐라는 거예요. 어떠한 특징을 가지느냐. 즉 뭔 얘기냐면 so when we are given arbitrary matrix A, we want to understand characteristic of the matrix A. Characteristic of the matrix A. This is the eigenvectors and eigenvalue, which is one of the most essential topics or the concept in this semester. Okay, this is overview. Let's suppose that here is the vector x defined here. So let's say this arbitrary vector x. Then let's suppose that we have an arbitrary matrix A. Then our new vector is going to be A times x. 그렇죠? A times x. Then all the vectors in this domain can be transformed to this domain. 그렇죠? Then when we transform original images like this, 그렇죠? Like this, by using a matrix A, arbitrary matrix A, let's suppose that it moved to like this. Then from here, how to understand this matrix A, or how can I expect original matrix, original image from here to move or transform looks like this. This is the eigenvectors and eigenvalues. In other words, what is eigenvalues, eigenvectors, eigenvalues, eigenvectors? Let's suppose that we have a matrix A. 3, 1, -2, 0. Let's suppose arbitrary matrix A. And let's suppose that we have a two vectors. U is equals to -1, 1, and V is equal to 2, 1, 2, 1. Then let's talk about U, A times U, and A times V. A times V. First of all, okay. So U is like this, 그쵸? -1 times 1, and V is equal to 2 times 1. Here and here. Then AU, A times U, it's going to be, in this case, AB. Here. AB. And AU, if you compute this one, AU, it's going to be new vectors like this. New vectors like this. In this case, there are very, very interesting things happens. AV equals to scalar multiple of original matrix V. In other words, AV is going to be just 2V, just 2V. And AU was not equals to scalar multiple times vector U, vector U. So in this case, to understand what happens by multiplying when we multiply matrix A to the arbitrary two-dimensional vectors U or V or X, this one, vector V, it's the more important than vector U because AV it's going to be V times scalar value 2. In other words, okay, let's go back to here. When we multiply matrix A to the arbitrary input vector, for example, like this one, or this one, or this one, or this one, or this one and this one, by multiplying matrix A, these matrices, these vectors can be moved to the arbitrary like this. But there exist two vectors, V1 or V2. In this case, transformed vectors A V1, it's going to be just a scalar multiple of the original vector 1. It looks like this. Or A V2, it's going to be lambda 2 times V2. V2. Like this. So when we considering this unit circle, transformed vector, it's going to be ellipsoid like this, right? So in this case, how can we find out? How can we expect the output shape from this matrix A? As you can see here, if we just consider vector V and vector V1 and V2 with scalar value lambda 1 and lambda 2, then you can easily expect output shape of transformed output shape by matrix A. In other words, V1 and lambda 1 and V2 and lambda 2 can be characteristic, can describe the characteristic of the matrix A. In this case, this one is called eigenvectors, and this one is called eigenvalues. In other words, if you can find out eigenvectors and eigenvalues for the arbitrary matrix A, you can say all the things about transformed field by matrix A. That's why we have to study eigenvalue and eigenvectors. 자, 이게 이제 컨셉추얼한 얘기라서 이제 조금 길게 설명을 하고 있는데 한국말부터 설명할게요. 자, 아이겐밸류, 아이겐벡터. 이제 뭐 뒤에 푸는 거는 쉬워요. 그냥 막 쭉쭉쭉쭉 계산하는 거 풀면 되고, 여러분들 그냥 뭐 풀 줄 알면 돼요. 어떤 매트리스 A가 주어졌을 때 아이겐밸류, 아이겐벡터 풀 줄 알면 되는데, 의미가 뭐냐? 이 아이겐이라는 의미는 characteristic, 특징, 한국말로 하면 특징이에요. 그래서 어떤 매트리스 A의 특징이 뭐냐를 말하고 싶을 때 이 아이겐벡터가 중요한 거예요. 뭔 특징이냐? 자, 우리가 이번 학기 뭐 배우고 있어요? A equals B에서 결국 이 AX가 어떤 트랜스폼으로 이루어진다고 얘기를 했었죠. 그렇죠? X를 어떤 AX라는 필드로 보내는 매트리스 A에 대해서 얘기를 하고 있는데, 그 A에 대해서 우리가 A의 특징을 알고 싶은 거예요. 근데 그 특징을 알려고 보니까 여러 가지 방법이 있죠. A라는 매트릭스를 막 분해도 해보고, 그쵸? 우리가 QR로 분해도 해보고 LU도 분해를 해봤는데, 또 다른 방법으로 한번 이해를 해보고 싶은데, 그 특징, characteristic 또는 eigen, 그쵸? 를 이해해보고 싶은데, 어떤 걸 이해할 수 있냐면, 어떤 X들을 어떤 인풋 X들을 막 A로 보내봤을 때, 어떤 유닛 서클에 있는 애들이 뭐 이렇게 타원형으로 바뀌는데, 그때 왜 타원형으로 바뀌는지를 말해줄 수 있는 건 이 벡터, 어떤 벡터인데, 그 벡터는 그냥 스트레치만 되는 거예요. 즉 어떤 람다로 뭐 스칼라 멀티플을 그냥 곱해서 나오는 벡터로 스트레치만 된다는 거 알면, 우리는 이 타원형이 요렇게 그냥 바뀐다라는 거를 쉽게 알 수 있고, 그 말은 뭐냐? 요렇게 생긴 유닛 스피어가 요렇게 바뀐다는 걸 알 수 있는 거죠. 그렇죠? 그 말은 뭐냐? 우리가 이제는 이 A에 대해서 언더스탠딩 할 수 있다라는 거고, AX가 어떻게 변할 수 있을지 예측할 수 있다는 거죠. 뭐만 알면? 아이겐벡터, 아이겐밸류만 알면. 그렇죠? 그래서 이제 우리가 아이겐밸류, 아이겐벡터 알면 우리의 매트리스 A에 대해서 모든 걸 다 얘기할 수 있다라는 거예요. 즉 캐릭터리스틱을 얘기할 수 있다라는 거죠. 이게 바로 아이겐벡터스 앤 아이겐밸류스라는 거죠. 퀘스천. 자, 오늘은 제가 좀 질문을 안 받고 오고 있는데, 자, 한번 보고 갑시다. 자, question so far or question about eigenvectors and eigenvalues. Or let me give some comment on these eigenvectors and eigenvalues. 자, 여러분 이제 우리가 말했지만 렉처 노트로 치면 2강 남았어요. 그렇죠? 그래서 요거랑 이제 다음 시간 이 SVD까지 하면 이제 이번 학기 마치고 이제 우리 또 기말고사까지 보죠. 그렇죠? 그래서 이제 후반부에 어떻게 보면 가장 중요하면서도 어떻게 보면 여러분들이 아마 지금까지 이제 배워왔던 컨셉들의 어떤 그런 뭐랄까요, 서머리에 가까운 이제 2가지 컨셉을 배우고 있어요. 그래서 아이겐벡터, 아이겐밸류스, 그 다음에 얘의 제너럴라이즈 버전인 싱귤러리티 디컴포지션에 대해서 이제 얘기를 나눌 거고요. 그 첫 번째로 도대체 아이겐벡터, 아이겐밸류스를 왜 배워야 되느냐, 얘의 의미가 무엇이냐에 대해서 지금 얘기를 해보고 있습니다. 그렇죠? 자, 여기까지 일단 질문이나 혹시 뭐 궁금한 거나 한번 우리 얘기를 해보고 갑시다. 우리 한번 질문을 한번 해봐야죠. 누가 있을까요? 형민 학생? 혹시 여기 이해되나요? 지금까지? 정웅 학생? 기억나는 친구들 혹시 여기까지? 오케이. 누가 있었지? 예담. 내가 맨날 물어보는 친구가 물어보는 것 같은데. 이 학생 이해되나요? 여기까지? 어렵지 않았죠? 어려울 거예요. 사실 어려운데. 네. 오케이. 이렇게. 다른 친구들? Others? So, here, understanding the meaning of the eigenvectors and eigenvalues is very important than comparing eigenvectors and eigenvalues, right? To compute eigenvectors and eigenvalues, you can just use some predefined equation. 그렇죠? Then, in your final exam, you can just use that equation to solve to compute eigenvectors and eigenvalues for the arbitrary matrix A, right? But you have to understand the meaning of that eigenvectors and eigenvalues. Okay. All right. Let's dive into the eigenvectors and eigenvalues. So here's the definition. Eigenvectors of the matrix n by n matrix is a non-zero vectors A such that Ax is equals to lambda x for scalar lambda. In this case, the scalar lambda is called eigenvalues of matrix A. If there is non-trivial solution of x of As equals lambda x. Such an x is called eigenvectors corresponding to lambda. Again, A equals lambda x. The solution the vectors that satisfy Ax equals to lambda x is called eigenvectors, and in this case, this scalar lambda is called eigenvalues. If there exists a non-trivial solution x, Ax equals to lambda x, then in this case, x is called eigenvectors corresponding to lambda. This is just a definition. So, this is just definition. So here, lambda is an eigenvalues of the n by n matrix A if and only if equation A minus lambda Ix times 0 has a non-trivial solution. In other words, from the here, Ax is equal to lambda x, we can derive this equation, 그렇죠? Ax minus lambda x, which is going to be A minus lambda I times x equals 0, 그렇죠? So, in this case, if this matrix has non-trivial solution, I mean the x is not equal to 0, then there exists eigenvectors and eigenvalues, lambda. In other words, let's say this is equation 1. In other words, the set of the whole solution of this one, 그렇죠? Equation 1. Set of the whole solution is just null space of matrix A minus lambda I, 그렇죠? Solution of this one is the null space of this matrix. So this is just the definition. So the set of the subspace of the Rn, this set is subspace of Rn because this is a null space, 그렇죠? Which is called Eigen space of A corresponding to lambda. This is just definition. Solution set, in other words, solution set of this equation is called Eigen space corresponding to lambda, for the arbitrary lambda. In other words, eigenspace, this one, eigenspace consists of zero vector because this is the null space, so this is subspace, so it has zero vectors, and eigenspace consists of the zero vectors and all the eigenvectors corresponding to lambda. In other words, In other words, if we already know eigenvalues lambda, we can solve this equation. Then Eigen Space is a solution of this equation, right? So the solution is going to be the eigenvectors for the corresponding eigenvalue. This is just the definition of the eigenvectors and eigenvalues. 예, 그래서 우리 어떤 람다라고 하는 게 우리 매트릭스의 이 아이겐밸류라는 걸 일단 알면 let's talk about how to find out this lambda later. But in this case, if we already know lambda as eigenvalues, then we can find out eigenvectors corresponding to lambda by solving this equation a minus lambda I times x equal to 0. So this is just a definition. Let me solve example. It's very, very easy. It's very, very easy. We can just use this equation. 그렇죠? 자, 푸는 건 정말 쉬워요. 근데 말했지만 푸는 거 그냥 갖다 풀면 돼요. 그러니까 막 설명이 어렵게 돼 있는데 푸는 거는 그냥 수식 갖다 풀면 돼요. 말했지만 이해를 해야 돼요. 왜 그런지. So, let me show you example first. Show that 7 is eigenvalues of matrix A, 1, 5, 6, 2, find the corresponding eigenvectors. So, first of all, scalar 7 is eigenvalues of matrix A if and only if Ax equals 7x has a non-trivial solution. 그렇죠? Let's say this is the equation 2, but this equation 2 is equivalent to the Ax minus 7x, 그렇죠? Equals 0. In other words, A minus 7i x is equal to 0. Right? So A was the 1, 5, 6, 2, 7 identity matrix. It's going to be 7, 0, 0, 7, which is going to be negative 6, 5, 5, negative 6. So from here, let's say this is the two column vector A1 and A2, A1 and A2. Columns of this matrix is obviously linearly dependent, 그쵸? Linear dependent. Why? A1 is equal to negative A2죠. 그냥 뭐 간단히 생각하면 linear dependent. So let's say this is equation 3. Equation 3 has non-trivial solution because they are linearly dependent. So there is the non-trivial solution. For example, because A1 plus A2 equals 0, so non-trivial solution is going to be the 1, 1. So anyway, it has a non-trivial solution. So because this one has non-trivial solution, this scalar 7 is eigenvalues of matrix A. Then how to find out corresponding eigenvectors? Let's just solve this equation. 그렇죠? Because we already know this matrix was 0, 6, 5, 6, negative 5. Then you can solve x by solving this homogeneous system. How can you do that? Let me use the low reduction algorithm. Negative 6, 5, 6, negative 5, 0, 0 from this equation, matrix equation. We can low reduce this one. Looks like this. And here, let's say here's x1 and x2. This is the free variable. x2 is a free variable. Then our solution is going to be x2 plus 1, x2 times 1, 1. 그렇죠? Why? From here, we can have x1 plus x2 is equal to 0. So we can derive this one. x1 is equal to negative 1. So x1 is equal to x1 and x1 is equal to x2, x2 is equal to x2, so x2 times 1, 1. This is just general solution of this homogeneous system. 그렇죠? 그쵸? 이게 제너럴 시스템과 우리가 알고 있는 이 homogeneous system이죠. Let's say this is kind of homogeneous system. homogeneous system. So this is the general solution of homogeneous system. So each vectors of this form with x2 is not equal to 0 is eigenvectors corresponding to lambda is equal to 2. Lambda is equal to 2. So in other words, eigenvectors of these eigenvectors corresponding to lambda is equals to can be x2 times 1, 1, for example, just 1, 1, if the x2 is equal to 1, or 2, 2, or 5, 5, 5, blah, blah, blah. These vectors, eigenvectors corresponding to lambda equals 7. This is eigenvectors and eigenvalues for the original matrix A. Matrix A. This is the definition of the eigenvectors and eigenvalues. Question. This is just the definition. You can just follow the just definition. 그렇죠? 근데 이제 뭐 여러분 좀 어려운 게 아니고 그냥 definition이에요. eigenvector, eigenvalue라고 하는 게 우리가 원하고자 하는 프로퍼티 아까 이런 프로퍼티를 만족하는 이 벡터와 이 스칼라 값을, 이 멀티플 값을 찾고 싶었기 때문에 이러한 데피니션으로 우리가 아이겐벡터, 아이겐밸류 정의를 내렸기 때문에 그냥 이렇게 따라서 풀면 되고, 이때 풀 때 뭘 쓰면 되냐? 우리가 지금까지 배웠던 호모지너스 시스템과 호모지너스 시스템 솔루션, 즉 널 스페이스를 찾았던 호모지너스 시스템 솔빙 스킬을 그냥 갖다 쓰면 돼요. 그래서 이렇게 아이겐밸류, 아이겐벡터를 찾을 수가 있다라는 거죠. 그렇죠? Question? No? Okay. So let me consider larger matrix 3x3 case. Yeah. Let's suppose that your matrix A consisting of 4, 2, 2, negative 1, 1, negative 2, 6, 6, 7. And let's suppose that eigenvalues of matrix A is 2. Find the basis for the corresponding eigenspace, or the set of the vectors in this corresponding eigenspace is called eigenvectors. So question is, let's find out eigenvectors corresponding to eigenvalues 2 for this matrix A. This matrix A. Okay. So, in other words, from the definition, corresponding eigenspace can be the null space of this one, A minus lambda I times x is equal to 0. So, in other words, homogeneous solutions, a solution of the homogeneous system, A minus lambda I times x is equal to 0. This is the corresponding eigenspace. So let's do that. First of all, matrix A was the blah blah blah, and I times in identity matrix is going to be 2, 2, 2 here. So then this one times this one minus this one is going to be 2, 2, 2, negative 1, negative 1, negative 1, 6, 6, 6. And then let's row reduce the augmented matrix for the A minus 2i, where this one was 2, 2, 2, negative 1, negative 1, negative 1, 6, 6, 6, x 0. We can make augmented matrix like this. Then we can row reduce this one to do like this. At this point, so let's suppose that x1, x2, and x3 are here. x2, x3 are free variables. So let's say free variable. Then we already know general solution of this case can be 2x1 minus x2 plus 6x3 is equal to 0. So x1 equal to 1 over 2 x2 minus 6x3. So our general solution can be x2 times 1 over 2, 1 over 2 here, 1, 0, x3 times -3, 그렇죠? -3 here, 그래서 -3, 0, 1. So this is our general solution because x2 and x3 are free. 그렇죠? x3 are free. So this one, 그렇죠? From this one, we already know these two vectors. These two vectors are 그렇죠? basis. 그렇죠? We already know this one, and this one is a basis for this solution space. 그렇죠? We already talked about this one in our solution set of the homogeneous system. 그렇죠? Now in this case, this arbitrary vector is eigenvectors corresponding to lambda is equal to 2. Is equal to 2. And basis for this eigenspace, the set of the whole eigenvectors is called Eigen Space. And basis for the eigenspace is going to be two vectors, this one and this one. This is eigenspace. Eigenspace. Okay. So what's the meaning of the geometric meaning of this eigenspace? So let me talk about here. Okay, so here, this is a 3x3 matrix. 그렇죠? This is 3x3 matrix. So it means that this 3x3 matrix can transform 3x1 vector to the another 3x1 vectors. 그렇죠? Let's suppose that you have an arbitrary vector in input space, 3D space, and multiplication by matrix A can transform arbitrary space, arbitrary three-dimensional space here. In this case, eigenspace means two-dimensional subspace of R2. In other words, like this. When lambda is equal to 2, your eigenspace was like this. 그쵸? Determined by this. 그쵸? 이거였죠? So when we draw whole paths of eigenvectors, it's going to be plane. Which plane? Determined by or spanned by 1 over 2, 1, 0, -3, 0, 1. So maybe two vector 1 over 2, 1, 0, and -3, 0, 1. Then this eigenspace is going to be the plane spanned by these two basis vectors. 그렇죠? In this case, when we consider the vectors in eigenspace, 그렇죠? Which is going to be eigenvectors, this vector is just be a stretch while having same direction. So this transformed vector transformed vectors still in eigenspace. In other words, this vector satisfying Ax equals to lambda x, where lambda is equal to 2. So 2. That's the properties. In other words, if you know eigenspace, eigenvalue and eigenspace of matrix A, you can easily expect vectors in eigenspace can still in eigenspace while they have the different magnitude. So this is the geometric meaning of the eigenspace. So in this case, anyway, in this case, the basis was the two vectors. 그렇죠? This one from here. 되돌아. 자, 우리 한 4분 남았는데 한국말로 한 번만 더 정리하고 넘어갈게요. 자, 무슨 얘기하고 싶은 거냐? 여러분들 어떤 3x3 매트릭스가 있어요. 그렇죠? 여러분들은 뭐 계속 알겠지만 우리가 치는 x 플러스 b. 그렇죠? ax 뭐였냐? 어떤 x를 a로 트랜스폼 했을 때 그 어떤 트랜스포메이트 그 리니어 트랜스포메이션에 대해서 이해를 해야 되는 건데 3x3이면 뭔 일이 일어나냐? 어떤 3x1 벡터를 다시 한번 3x1 벡터 스페이스로 이렇게 옮겨주는 역할을 하는 거죠. 근데 이때 무슨 일이 일어나느냐를 우리가 이해하고 싶은 거예요. 그렇죠? 근데 이 아이겐벡터, 아이겐밸류라는 걸 알면 어떤 특성이 있냐? 아이겐밸류와 아이겐밸류의 아이겐벡터, 아이겐밸류의 가장 큰 프로퍼티는 ax is equal to lambda x, 즉 어떤 이 아이겐벡터는 그냥 아이겐벡터 자체를 람다라는 스칼라로 곱한 거가 이 a가 트랜스포즈가 된 거랑 똑같다. 트랜스폼드 된 거랑 똑같다. 라고 하는 프로퍼티를 가지니 뭘 할 수 있냐면 아이겐 스페이스 저 어떤 코레스펀딩하는 람다 아이겐밸류의 아이겐밸류로 결정나는 이 아이겐 스페이스 안에 존재하는 모든 아이겐 벡터들은 우리가 잘 모르지만 매트릭스 A를 통과하고 나면 그래도 이 아이겐 스페이스 위에 존재를 하면서 이때 아이겐 밸류만큼 이동을 하게 트랜스폼이 될 거다 라는 거를 우리가 알 수 있다라는 거죠. 그렇죠? 다시 얘기하면 뭐냐? 매트릭스 A를 가지고 트랜스폼이 일어났을 때 어떤 아비트러리 벡터 X를 매트릭스 A에 곱했을 때 무슨 일이 일어나느냐? 아비트러리 벡터 X를 A에 곱했을 때 무슨 일이 일어나는지 알기 위해서는 먼저 어떤 아이겐 스페이스 위에 존재하는 즉 아이겐 벡터들을 A에 곱했을 때는 이렇게 아이겐 스페이스 안에 여전히 존재하면서 아이겐 밸류를 곱한 매트릭스 벡터로만 바뀐다더라 라는 걸 프로퍼티만 알고 있다면 우리가 완전 아비트러리 벡터 X라고 하는 거를 A에 곱했을 때 어떤 일이 일어나는지도 설명할 수가 있을 거다 라고 하는 게 아이겐 벡터와 아이겐 밸류의 컨셉이고요. 그 아이겐 벡터를 어떻게 찾느냐 하면은 아이겐 스페이스를 찾아서 그때 베이시스를 찾으면 되는데 어떻게 찾을 거냐? 그냥 이러한 호모지니어스 시스템을 그냥 우리가 지금까지 배웠던 걸로 열심히 풀면 그 벡터를 찾고 나면 그렇죠? 그게 이제 바로 솔루션 셋이 되니까 아이겐 벡터를 찾는 방법이 되더라 라는 거죠. 그렇죠? 이게 이제 바로 Eigenvectors and Eigenvalues의 컨셉입니다. 오케이? Question. 자, 서현 학생, A를 사용변으로 봤을 때 고유 벡터는 사용변의 크게 반하고 방향 보존된 벡터이고 맞아요. 아주 정확하고요. 방금 서은 학생이 말씀드렸던 네, 정확합니다. 한국말로 그죠? 고유 벡터라고 하죠. 한국말로 하면 정확한 표현이고 고유 벡터는 크기가 변화하지만 방향이 보존되는 걸 고유 벡터라고 하고 그때의 변화값을 고유값, 그죠? 아이겐 밸류라고 하는 거예요. 그죠? 바로 그거를 영어로 써준 게 바로 그냥 이거죠. definition. 그죠? 그죠? 아주 정확해요. 그죠? Any other question? No? Okay. So that's it. So in this lecture note 12, we started the eigenvectors and eigenvalue. Next time, in the next lecture, we will talk about how to find out eigenvalue and eigenvector in more efficient way. And let's talk about eigenvalue factorization, which is another factorization compared to the value factorization and QR factorization. Okay? No more question? Okay, so that's it. So this is the end of today's lecture. Thank you very much. Please remember that I will uploaded today's lecture in our YouTube channel. Please recap or review if you not fully understand. Yeah? Okay? Then please review and let's take a next lectures. 오케이? 자, 여러분 이제 우리 오늘 여기까지 하고요. 여러분들 아마 이제 조금 어려운 내용들이었을 수도 있을 것 같아요. 아마 앞에 내용들을 좀 여러분들이 복습을 안 했다면 복습. 자, 여기 지금 다 강의 올려놨죠? 복습 꼭 하시고 제일 어려운 내용들이면서도 제일 중요한 내용이면서도 뭐라 표현할 수 있을까? 이번 학기 이제 리니어 알제브라 파트의 이제 마지막 불꽃일 거예요. 아마 좀 어렵겠지만 여러분들이 조금만 더 신경 써서 공부해서 이제 이번 학기 잘 마무리 해보도록 합시다. 알겠죠? 자, 여러분들 오늘 너무 고생했고요. 우리 이제 목요일날 다시 보도록 합시다. 고생하셨습니다.